Hi, I'm Ryan Kristen, veteran fire officer and fire service instructor. I'm here to talk about Explotrain's explosive blast simulators and battlefield effects, specifically the science, safety, and dependability of their devices. In fact, it's that safety and dependability that led me to exclusively choose Explotrain to provide all battlefield effects for our mass casualty active shooter exercise, MCASE. The exercise involved 3 counties, included 19 organizations ranging from military, law enforcement, SWAT, fire, EMS, and even EOD teams. Since 1998, Explotrain has utilized a combination of gases to achieve their explosive blast effects. These gases commonly include oxygen and propane. Now, the cylinders used may look different from these, but these are representative of those products. Before we talk too much about the science behind Explotrain's devices, it's important to understand the chemical properties of these gases. Propane in a pressurized container exists in both gaseous and liquid phases in a state of equilibrium. The pressure of the gas to maintain this state of equilibrium depends on the temperature of the propane. As the temperature increases, the pressure required to maintain this state of equilibrium increases as well. For example, at 30 degrees Fahrenheit, the equilibrium gauge pressure is 51 psi, while at 80 degrees Fahrenheit, the gauge pressure would increase to approximately 128 psi. When propane gas is removed from a pressurized cylinder, the pressure in the cylinder drops due to the removal of the propane, and the temperature in the cylinder decreases due to adiabatic cooling. The new equilibrium pressure will then be lower as a result. As the propane in the cylinder warms back up and returns to ambient, the equilibrium pressure will return to its original level as well. However, if propane gas is removed from the cylinder again, the temperature and pressure will once again decrease. This pressure-temperature relationship comes into play with Explotrain simulators when they are operated at extreme temperatures or repeatedly fired for several times in rapid succession. The pressure regulators used to supply the propane and oxygen to the sound chamber will reduce the delivery pressure to a constant level, regardless of the pressure within the gas cylinder. However, in extremely cold conditions, this equilibrium pressure may be too low to provide enough propane through the regulator for the simulator to function properly. To counteract this, Explotrain's XO series simulators individually control the oxygen and propane valves, allowing them to automatically maintain the proper level of propane in the sound chamber by opening the propane valve longer as the temperature decreases. This extended valve opening allows the proper amount of propane to pass through and into the sound chamber at low temperatures, even as the equilibrium and therefore delivery pressure drop below optimal levels. None of these methods are needed for oxygen, since it is supplied from its cylinder in a purely gaseous state. Another important principle of both oxygen and propane is their specific gravity. All gases have a specific gravity relative to air at standard temperature and pressure. The air we breathe is given a rating of 1. Propane has a specific gravity of 1.55, and oxygen a specific gravity of 1.105. Since both of these gases have a specific gravity heavier than air, they will tend to sink in air and accumulate in low-lying areas. Now that we have a better understanding of these gases and some of their chemical properties, let's take a look at how Explotrain utilizes them in their explosive blast simulators and battlefield effects. We'll start with the XCAL, Explotrain's machine gun simulator. Since the X-Cal fires several shots per second, requiring millisecond control of propane and oxygen fill times, it is particularly sensitive to variations in delivery pressure. As we saw earlier, propane delivery can be very dependent on temperature. To combat this problem, Explotrain utilizes an integral expansion chamber as part of its cold fire technology. The expansion chamber of the X-Cal creates a reservoir of pressurized propane in its gaseous state. When fired, the small amounts of propane are drawn from this reservoir rather than the much smaller volume of just a supply hose. The corresponding drop in supply pressure is significantly smaller as a result, typically only about 3%. The benefits of the pressure reservoir are most notable when the X-Cal is subjected to changes in ambient temperature. As the equilibrium pressure of the propane changes with temperature, the cold fire reservoir acts as a buffer, providing a much more consistent delivery of propane gas, ensuring consistent operation over a wide range of temperatures. The X-Cal machine gun simulator is the only simulator on the market capable of simulating different caliber or model weapons through the use of interchangeable barrels and adjustable firing rates. Some other models claim to be able to simulate various weapons just by adjusting the firing rate. However, as anyone with any experience with firearms would know, adjusting the fire rate of an M4 5.56mm simulator from 800 rounds per minute to 500 rounds per minute won't make it sound like a 50 caliber M2. It will just sound like a slow firing M4. The interchangeable barrels of the X-Cal simulator are different lengths and diameters to produce the different harmonic frequencies and tones of the more commonly used rounds on the battlefield. This includes 5.56, 7.62, and of course, everyone's favorite, the 50 cal. Just as in the X-Cal machine gun simulator, the same design precision and safety engineering goes into every Explotrain device. Explotrain explosive blast simulators utilize a dry fire block system that helps to eliminate misfires from moisture accumulation and controls gas mixtures. This dry fire block places the firing plug in a position to ensure maximum performance. This dry fire block is a design unique to Explotrain that ensures dependability. To better illustrate the safety and design features of Explotrain's devices, we're going to conduct a couple of experiments utilizing these replica devices to help illustrate the function of these simulators. It should be noted that these experiments are being conducted under safe conditions with appropriate personal protective equipment, and under no conditions should you attempt to replicate these experiments yourself. Both devices fire in a similar manner, utilizing a spark plug as the ignition source. As we've shown, the Explotrain firing plug is encased in a dry firing block on the side of the chamber. Originally, devices placed the firing plug in the bottom of the cylinder. Also, the Explotrain device allows the gas to enter directly through the dry fire block, where the gases mix, pass directly over the firing plug, and spread into the detonation chamber. Other devices have the gas enter through the chamber on the side and rely on vapor density to allow the gases to sink to the firing plug. Under ideal conditions, in the perfect environment, both devices function in a similar manner. In this experiment, we've added a small amount of propane to each device, and we witness a small controlled burst. However, in anything less than ideal conditions, we see dramatically different results. As moisture accumulates in the devices from rain, dew, humidity, or other sources, we see that the competitor devices cannot fire, while Explotrain devices continue to deliver the consistent, dependable performance they're known for. In this next experiment, we use an actual Explotrain dry firing block and electronic ignition system. Here, you can see the spark plug is completely saturated. This moisture prevents the firing of the plug, as it would in any device. However, using nitrogen, a non-flammable gas, to simulate oxygen and propane entering the block, you can see the moisture is immediately purged from the system. As the gases pass over the firing plug, the ignition source is dry, and the firing plug is allowed to fire with consistent dependability. To further illustrate the effectiveness of the dry fire block to purge moisture, we've placed the dry fire block system under blacklight conditions in this NDT chamber and apply antifreeze to represent accumulated moisture. Again, we see, as the air pressure is passed through the block, the firing system is purged and the plug is cleared to fire.
The intent of simulated warfare, or effective field training, is to create an environment where mistakes are frightening enough, real enough, and intense enough that it effectively prepares the trainee for the real world.
A hazard resulting from real explosives is blast overpressure. This is the sudden increase in atmospheric pressure that is created by the wave of rapidly expanding gas in an explosion. This blast overpressure is commonly known as a shock wave. This shock wave is an initial blast of positive pressure, followed immediately by a brief negative pressure as the atmosphere stabilizes back to ambient conditions. This wave illustrates an ideal blast overpressure waveform. Explotrain devices produce a safe, realistic, and carefully controlled blast overpressure. This graph illustrates actual readings of blast overpressure recordings from an Explotrain simulator. As you can see, the Explotrain device produces a similar effect to actual explosives. This effect, however, occurs at safe levels. Physiological damage to air-filled organs can occur with surprisingly low pressures. Basic personal protective equipment, specified by DoD standards, provides appropriate protection for safe training. All Explotrain devices utilize automated temperature compensation and design principles to ensure that not only are blast overpressures sufficient enough to create realistic training, but safe enough to protect from injuring trainees.
Blast overpressure is just one aspect you need to consider when selecting a training device or explosive simulator. Another aspect is to consider the training environment itself and your objectives. Now we're going to take a look at Explotrain's XOMG, their largest available explosive blast simulator, and we're going to see why size matters.
Many of the other improvised explosive simulators on the market rely on adding more gases to the cylinder for a larger blast effect. The problem with this is that the detonation can only reach a certain volume before creating unsafe conditions. As we have shown, propane and oxygen will sink in air. Simply adding more gases to create a larger blast can become dangerous. As the gases fill the firing chamber, they displace the air in the cylinder. At a certain point, the gases accumulate to the point of spilling out of the chamber. This, under the best circumstances, wastes product and increases operating costs, while adding no additional effect. Under the worst conditions, the gases can spill over the cylinder and pool in low-lying areas around the device. This accumulation could create possibly hazardous conditions. The only way to safely and effectively replicate large explosions is to use a device designed and tuned to produce such effects. Explotrain's XOMG is perfectly suited for large explosive simulations.
Explotrain's designs ensure the dependability and safety that we need for effective field training.
In addition to controlled gas releases, Explotrain ensures additional safety through design and engineering. The gas cylinders are stored securely outside of the electronics enclosure, on the X-Cow, and on the IED simulators. In addition, the electronics are encased in a vented safety enclosure to prevent the buildup of flammable gases inside the casing. Other improvised explosive simulators store the gases and electronics in a non-vented enclosure. The accidental release of gas within the enclosure may create a dangerous condition. As we've seen, the gases used are heavier than air. Thus, a leak into an unvented case could result in the buildup of gases within the electronic circuits. An accidental activation or even a static discharge from a user could result in unexpected and potentially dangerous combustion.